So we're going to begin a new unit today on rational functions. We've looked at linear and quadratic functions. We've looked at radical functions. We've looked at exponential and logarithmic functions. So now we're going to spend some time looking at rational functions. And the topic for today is inverse variation. So we're going to be able to identify a difference between a direct and inverse variation, and then write functions that model either inverse or direct variations, and also be able to describe something called a combined variation, where we may have a function that has both variables that vary inversely and variables that vary directly. All right, let's look at a little example here so we can better understand what inverse variation looks like. How long would it take you to ride 24 miles at different speeds on your bicycle? So we're going to fill in this chart and graph it. If we were riding at 2 miles per hour, right, how long would it take us to go 24 miles? Well, we're going to take the distance, 24, and divide it by the speed. We would get 12. If we were going 3 miles per hour, right, 24 divided by 3 gives us 8. We'll plot these points as we go here. If we were going 6 miles an hour, 24 divided by 6 gives us 4. And 12 miles an hour, we will travel that distance in 2 hours. And at 24 miles per hour, it will take us 1 hour. So if we try and put a line through those, or fit a curve through those points, right, we get this smooth curve that looks a little bit like a decay function, but in reality, this is a graph of inverse variation. There are some differences. Notice it does not cross the y-axis like a decay function did. So let's let our bike rider continue on here. So this is an example of inverse variation. Now, why do we say inverse? Because the two variables involved here, speed and time, vary inversely with each other, which means if the speed were to increase, the time decreases, or vice versa, right? If the speed decreases, the time is going to increase. But basically, as one variable gets larger, the other gets smaller, or they move in opposite directions. So that's how we define inverse variation. So we can write a function for the inverse variation between speed and time. So if we look at our graph here, let's label some things. The y-axis was time, and the x-axis is speed, right? So, and the distance was a fixed quantity, right? We did all this analysis for the same distance of 24 miles. So let's plug those variables in. We're going to put in y for time, x for speed, and our constant of 24 miles for distance. So we have a special name for that constant. We call it the constant of variation. And for a given constant, right, we get corresponding values of speed and time, where as one increases, the other decreases, or vice versa. We could also rearrange this equation to solve for x, right? So we can write this really two ways, either solving for y or solving for x, or we could write it a third way, where we put x and y on the same side, and notice x times y equals our constant of variation. So if we have a value for x and a value for y, we can simply multiply them together and get our constant of variation if they vary inversely. All right, so let's look at an example here. If I gave you some data, we'll use the same data we did in our first example. Can we model it as a inverse variation? So what is the constant of variation for the bike ride data? So remember, x is our rate, our speed, y is our time. So we can pick any 2 points here, 6 and 4. So we're going to multiply those x and y values, or in this case, rate and time, together to get our constant of variation. And then we can plug in that value of 24 for k into our function, Remember, we can write it three ways. This is one way, x times y equals 24. Or here's the other way, solving for y. All right, so in summary here, inverse variation, right, is where as one variable increases, the other decreases. And we will use the common form y equals k over x with that constant of variation. Direct variation, we've actually studied already. Those are linear functions that vary directly. So as x increases, y increases. And we can write that y equals k times x rather than k divided by x. And the k is basically the slope of that line for direct variation. All right, let's look at an example here. I'm going to give you some x and y data, and I want you to determine two things. One, does it vary inversely or directly, or neither, and then write a function to model the variation. So first, how do we tell whether or not it's direct or inverse variation? Well, let's look at how the values change. In this case, x values are increasing, 1, 2, and 6. How about the y values? They also are increasing, right? 3, 6, 18. So if they're both increasing, then we would say this example is direct variation. Now, we need to find our constant of variation k in order to write the function. So we'll start with this form, y equals kx, and we're going to solve for k. So we simply take any y value and divide it by x. So let's do it for all three values. And this is important when we're testing to see if it's direct variation. We can always find a k value for any single pair of x and y data, but to confirm that it is direct variation, we should get the same k value for all pairs of x and y data. So 3 divided by 1, 6 divided by 2, 18 divided by 6, they all give us the same value of 3. So there's our equation for direct variation, y equals 3 times x. Let's try another one, see if you can determine here whether it's direct or inverse. All right, so x is increasing, 1, 2, 6, but notice now y decreases, 18, 9, and 3. So we have inverse variation, but let's confirm that by solving for k. So here's the form we're going to use for inverse variation to solve for k. X times y equals k. So let's plug in all of our values, 1 times 18, 2 times 9, 6 times 3, and we see that we get the same constant of variation, 18. So let's plug that into our equation. This would be our function, x times y equals 18, or we could write this as y equals 18 divided by x. Right, let's try another one. See if you can take this all the way through now. All right, x increases, as does y. So this is direct variation. So let's test our values and divide the y values by the x values. So if we do that, we'd have to simplify these fractions, but we would see that we get a k value of 3 over 2 or 1.5 if you did it on your calculator. And there is our function. We're going to plug that 3 over 2 back in for k. All right, one more, 0.5, 2, and 5. So x is increasing, y is decreasing, 4, 1.4. So we have inverse variation, but let's figure out our k value and confirm it's the same for all sets of x, y data. So if we multiply these together, we're going to get 2 for each result. So it works. This is an inverse variation where x times y equals 2. All right, actually I lied. Here's one more. So x is increasing, y decreases, so it appears to be inverse variation, but let's confirm that. We're going to find our k value by multiplying the x and y values together. Right? So if we do that, we get 1.4. All right. Oh, we do have one more. Okay. X is increasing, 1, 2, 3. Y is decreasing, 2, 1, and 0.5. So let's plug those values in. It appears to be inverse variation. So we're going to multiply them together. Now here, notice the first two give us a k value of 2, but the third, 3 times 0.5, gives us 1.5, not 2. So we don't have the same k value. Therefore, it appears to be inverse variation, but in fact, it's not, because we do not get the same constant of variation k for all values. So we can only say that this is neither direct or indirect. Now, let's look at the last topic here, using combined or other variations. So quantities can vary with respect to each other in different ways. So for example, how would we describe this function and how it varies? Well, we could say y varies directly with x cubed. Right? Our constant of variation k is multiplying not just x, but x cubed. Or in this example, we would say y varies inversely with z squared. Right? If we're dividing by a variable on the right-hand side, then that will give us an inverse variation. If we're multiplying by k by the variable on the right-hand side, that gives us direct variation. So we can put more than one together in the same function. So z equals k times x times y. Now notice we're multiplying both x and y times the k value. So here's one way we could describe this with words. Z varies directly with the product x, y. Or you could say z varies directly with x and varies directly with y. You could describe it either way. Let's try another one here. Same as above, but now notice we've added w. We're dividing by w. So we're going to have both direct variation with the product of x and y and inverse variation with w. And let's look at another one. Z equals k times w divided by x and divided by y. So w is multiplying k, so that's going to give us a direct variation. So z varies directly with w. And we're dividing by xy, so that's going to give us the inverse variation with the product of xy. All right, let's see if you can describe these in words here. Just pause it and then continue. So y varies inversely with z squared. K varies directly with y squared. X varies inversely with the product of w and z. Z varies directly with the product of x, y. All right, let's look at one more type of problem and then we'll wrap this up. So it says, suppose y varies inversely with x. We want to write a function that models each inverse variation, then find y when x equals 10. So we're actually being told that it's inverse variation. We don't need to try and confirm that, okay? So if we're told it varies inversely, we're going to start with our form of the function for inverse variation, y equals k over x. And we have to find the k value in order to write this function. So k we're going to find by multiplying x and y. So that's simple. 20 times 5 gives us 100. So now we're going to plug that 100 in for k, and we get our function, y equals 100 over x. Okay, we got that from being told it varies inversely, and we have one set of x and y values that we use to calculate the k value. Now the last part, it says find y when x equals 10. Well, that's easy. We just plug in 10 for x, do the math, and we get a value of 10. All right, let's try another one. So we're going to start with our general form, rearrange it to solve for k, then just multiply the two x and y values and we get 18. So here's our function, y equals 18 over x. Now we want to find y when x is equal to 9. So we plug that in and we get 2. All right, one more. Multiply our x and y values, we get a k value of 72. We plug that into our function. And now it wants us to find y when x is equal to 6. So we plug that in, we get a y value of 12. Now, it gets a little more complicated here. Suppose y varies directly with x and inversely with z. So we want to write a function. So here's what that would look like, right? Directly with x, so we're going to multiply k times x. Inversely with z, we're going to divide k by z. And notice they give us values for y, x, and z. They have to give us all three values in order to find the k value. So let's plug those in, right? I rearranged this, notice, to solve for k by multiplying by z and dividing by x. That gets k by itself. And then I plug in the values and I see I get 4. So here's our function, y equals 4x divided by z. And then it says find y when x is equal to 6 and z is equal to 2. So we're going to plug in 6 for x, 2 for z, and we get 12. All right, that's it. So we know how to identify functions that vary directly or inversely. We know how to write the functions to model that inverse and direct variation. And we know how to work with combined variations where we may have both inverse and direct variation in the same function.